was an old man past his prime and just unable to accept the new theory of physics because it was too radical.
But 30 years later, one man stumbled across Einstein's forgotten paper when he realized something. The prediction could actually be tested. When scientists ran the experiment, they were shocked. Quantum physics really does break the universal speed limit.
We're obliged to invoke something like actions going faster than light from one place to another.
This is a video about one of the spookiest and most misunderstood experiments in all of physics. And it might even be the strongest evidence we have that we live in many worlds.
If the sun were to disappear all of a sudden, how long would it take until we noticed and were released out into space? Newton's theory says that gravity acts instantly across any distance, so if there's a change in gravity, we should feel it immediately. But Newton himself was disturbed by this. That one body may act upon another at a distance is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it.
But in 1905, Einstein realized action at a distance isn't just absurd, it leads to outright paradoxes.
Einstein had discovered that observers moving at different speeds can disagree about when events happened. Let's say you see two things happen at the same time. An observer speeding past would see it differently. To them, one of these happened first, and both points of view are equally valid. But in the case of gravity, this leads to disaster. Say you see the sun disappearing and Earth flying off at the same time, as Newton predicted. Then the other observer sees something impossible. They see the Earth flying off first, even while the sun is still there, and it should of course be pulling the Earth in. So to them, it looks like cause and effect are reversed. The only way out of this paradox is to reject the assumption we started with, so gravity can't be instant. It took Einstein 10 years to fix this issue, and in the process he completely overhauled our understanding of gravity. Gravity is caused by the bending of spacetime. When there's a change in gravity, that only affects the local spacetime, and then that ripple spreads out to nearby regions, which spread farther out until eventually they reach us. This theory of gravity is local because effects spread from place to place at the speed of light instead of being instant. From our frame of reference, if the sun disappeared, that ripple would take about 8 minutes to reach us. Another observer might disagree about the length of the delay, but now we all agree that the sun disappeared first.
This is why nothing can go faster than light. The delay between cause and effect ensures all observers agree on the order.
After Einstein fixed gravity, all of classical physics obeyed this important rule. But then, Einstein studied the new theory of quantum mechanics and made a terrible discovery. This is one of the most famous photographs in physics. It was taken at the 1927 Solvay conference, where the architects of the brand new quantum theory gathered to discuss it. Around 60% of the attendees would win Nobel Prizes, but Einstein thought they'd gotten something fundamentally wrong, and this was his chance to prove it. So he took to the stage with a thought experiment. Imagine you fire a single electron through a narrow slit toward a circular detection screen. Well, quantum mechanics says that this electron has some sort of wave associated with it, called a wave function, which spreads out through space as it travels. When the electron hits the screen, you detect it at a single point. Where it turns up depends on the amplitude of the wave. If the wave is very big in a particular area, the electron is more likely to turn up there. Let's say it appears here. So far, everyone was following. This is what quantum mechanics predicts. But Einstein's next question surprised them. Why doesn't the electron turn up at this other spot a moment later? There's only one electron, so we can't detect it twice. But the way quantum mechanics ensures this is that when the electron was detected at the first spot, its wave function collapsed to 0 everywhere else instantly. That's why the probability of finding it at the second spot is now 0. There's no longer any wave there. But Einstein asked the audience to think about what this means. The measurement here must instantly affect the wave function over here, no matter how far apart these locations are. In other words, quantum mechanics requires instant influences across distance. It violates locality. Einstein concluded his talk by saying this is an entirely peculiar mechanism of action at a distance, and that this implies to my mind a contradiction with the postulate of relativity. Einstein's argument was so simple and his talk so short that people didn't know what to make of it. One audience member said, "I feel myself in a very difficult position because I don't understand what precisely is the point which Einstein wants to make. No doubt it is my fault." That man was Niels Bohr, the most influential figure in quantum physics at the time. Bohr's institute in Copenhagen had become the hub for the new field. Dozens of young scientists like Werner Heisenberg came to learn from him. As one of his disciples remembers, Bohr had invited a number of us to his home where we sat close to him, some literally at his feet on the floor, so as not to miss a word. Bohr wasn't the one who wrote the mathematical rules of quantum mechanics. Instead, he told everyone what they meant. While others were confused by the theory, Bohr offered answers. His philosophy became known as the Copenhagen interpretation of quantum mechanics.
My general understanding of the Copenhagen interpretation is you have the wave function, it describes everything that you can know about a particle or a system, and it evolves according to the Schrödinger equation, and at some point you're going to make a measurement, and at that point the wave function collapses.
I think that one bit of that you said was like, the wave function is all you can know about the particle. And I think that was like a pretty important point to Bohr.
As Bohr would put it, it's wrong to think that the task of physics is to find out how nature is.
The job of physics is just to predict measurements in the lab, which quantum mechanics does incredibly well. As for what the electron is doing when you're not looking, well, to Bohr, that question didn't even make sense to ask. The wave function tells you everything physics can or should tell you.
Einstein couldn't stand the Copenhagen interpretation. In a letter to his ally Schrödinger, he called it a tranquilizing philosophy, or religion. Einstein felt his thought experiment exposed a critical weakness in the Copenhagen interpretation. He'd shown that the way the wave function collapses is non-local, and so he reasoned maybe the wave function is the problem. Maybe it's not the best way to describe the electron after all. He may not have convinced Bohr of this during his talk, but he was determined to do it during the rest of the conference.
Physicists tell a version of this story, that you will find in physics textbooks and in pop science books, and that, physicists tell amongst ourselves that what happened was Einstein and Bohr had a great debate, and Einstein was unhappy with quantum mechanics because it was fundamentally probabilistic. He tried to show that there were conceivable experiments that you could use to get around those uncertainty relations, and Bohr showed over and over and over again that you couldn't do that, and eventually everybody agreed with Bohr.
That's Adam Becker, author of What is Real, a great book about the history of quantum mechanics. As he explained to us, Bohr may have just misunderstood the purpose of Einstein's thought experiments. We have documented evidence of this in at least one case. Einstein described a thought experiment that involved a box of photons and a mirror. Its purpose was to show the non-locality of the Copenhagen interpretation in action.
Bohr just misunderstood it, and when he recounted it to others later on, he drew a little diagram of what Einstein's thought experiment setup was, and it just didn't have the mirror in it at all. And yet this is taken as like the great victory for Bohr over Einstein, which is crazy. But history is written by the victors, right?
To understand what Einstein was arguing for, think of the relationship between Newton's gravity and general relativity. Newton's theory works well in most situations, but in that theory, gravity is a non-local force, leading to paradoxes. This was the motivation for coming up with Einstein's general relativity, which is local. Einstein believed the same logic applied to quantum mechanics. His thought experiment revealed that quantum theory is non-local, so just like with Newton's gravity, quantum mechanics must not be the final theory. There must be a local one that will replace it. And as a bonus, he thought this new theory might even unify gravity with the quantum world.
It would be hard to imagine coming to the final theory right away, and the fact that you can see paradoxes like this would make you think there's got to be more to it that we just don't have yet.
Absolutely.
But Einstein hadn't even persuaded Bohr that quantum mechanics really is non-local. So in 1935, he made one last attempt to convince the community that there was a contradiction between quantum mechanics and relativity. With the help of two younger colleagues, Boris Podolsky and Nathan Rosen, he formulated another, even more striking thought experiment that shows the non-locality of quantum mechanics. This paper is now known as the EPR paper, after its authors. Here is a simplified version of their thought experiment. Imagine a single high-energy photon suddenly becomes two particles. One of them is an electron, and to conserve total charge, the other is a positron. Since one is negative and the other is positive, they cancel out. But both electrons and positrons have a property called spin, and like electric charge, this also needs to be conserved. If the light started out with zero spin, well then the two particles together must have zero total spin as well. For example, if the direction of the electron spin is this, the positron has to have spin in the opposite direction, so that they perfectly cancel out. But the electron spin could have been this instead, or this. All of these possibilities are valid, so the rules of quantum mechanics say that the electron does all of these possible things at once until it's measured. It's not just that we don't know what the spin is, the electron really is doing everything. The only restriction is whatever the electron is doing, the positron must do the exact opposite. This also means that when the electron is measured and its state is determined, so is the positrons. This is what we mean by entanglement. The two particles' states depend on each other. But how do we measure the particles and force them to do one thing? Well, for that, we use the Stern-Gerlach machine. It's essentially a strangely shaped magnet, and it's how we measure spin. The orientation of the magnets determines what axis you're measuring the spin in. For example, if the machine is like this, and we shoot in a particle with spin in the positive z direction, it will certainly go to this spot we'll call plus. If instead a particle has negative z spin, it will certainly go down to minus. So this Stern-Gerlach machine measures spin in the z-axis. So what happens when we put in one of our entangled particles? When the electron goes into this machine, it either goes to plus or to minus, with 50-50 probability. Let's say our electron goes to plus.